Okay, I'd like to look at the unit preparation problems for lesson 1. Now, what happens here is this little graph, this is kind of important. So the idea is we have 4 lines and it represents the 4 different chemicals in this equation. So the idea here is, well, which of these are the reactants and which of these are the products, and which ones have a 1 and a 2, which ones have a 2 and a 1. So those are the clues for how to identify these. Well, if we have a reactant, okay, you can expect that a reactant is going to begin with a high concentration and it's going to go down and down and down and down over time. So the downhill ones must be the reactants. And we have a 1 and a 2, okay, so that means the 2 is going to get used up twice as fast as the 1. So we can kind of say then that B must be this chemical, okay, because it's getting used up twice as fast. And A must be this chemical, the hydrogen, because it's going down, but it's not getting used up as fast. And we can kind of see that over a certain amount of time, we're using up this amount of chemical A, but over the same amount of time, we're using up, it looks like twice as much of chemical B. It actually looks like more. Okay, going the other way, if we're making these chemicals, okay, well then these chemicals should be going uphill, and here's a 2 and here's a 1, so we can see the 2 must be this one, and the 1 must be this guy. So the answer here, the question was, let me erase all this writing, I can't see what I'm doing. Okay, each of the following curves corresponds to one of the species. Identify the species that each curve represents. So let's go back here. We say, well, we have hydrogen. That's going to be a downhill, and it is going to be downhill not very much. So this must be the H2. Okay, the ICl is going downhill, but because there's 2 of them, it must be going down twice as fast. So let's color code. So that's that one. That's this one. Okay, the hydrogen, okay, must be going up because we're making it, and it's going up pretty fast because there's a 2, so that would be our C, HCl. And then D would be our iodine. It's going up, but not quite as fast, so that's our I2. Now, there are explanations, okay, that this guy is going down, okay, and that this guy is going down but twice as fast. Okay, the HCl is going up and twice as fast, and this guy is just going up. Next problem. Consider this reaction. The following data are recorded for the reactions collected. Okay, so fill in the chart. So we want the rate of disappearance of O3. Well, rate, we know, is defined as the change in concentration, in this case of O3, over the change in time. Change in concentration over the change in time. So from 0 to 1 second, okay, what's the change in the concentration of O3? That's the only one we have data for. And then what's the change in time? Well, the change in time is 1 second, obviously. So this is going to be over 1 second. And the change is going from 0.1 down to 0.091. And whenever we do a change, we always do final minus initial. So 0.091 minus 0.1. So that would be 0.009 molar. Okay, and this would be a negative because it's final minus initial. So we could say the rate of disappearance is negative 0.009 moles per liter per second. Now, if that is going away at 0.009, okay, then we can see, well, what's happening to the oxygen? Well, for every 2 of these that changes, 3 of these also change. So we can take this relationship, the 2 to 3, and we know that this guy must be appearing 1.5 times faster than our oxygen. So I'm just going to take this guy and multiply by 3 over 2. And when I do that, I'm going to stop and calculate that. And I get that this is 0.0135 moles per liter per second. Okay, so this one again, that is 1.5 times larger. This guy is 1.5 times larger than this one. Okay, now how about from 1 to 2? Okay, we'll just change colors. We'll change here. So here's our, I'm sorry, from 1 to 2, that's wrong. From the 1 to 2. Okay, so for the first one here, our oxygen, our O3, that's what we actually have data for. So for O3, oops, I covered it up. Okay, 0.083 minus 0.091. So 0.083 minus 0.091. Okay, all over again 1 second. So my rate comes out to be 0.008 over 1 second, so moles per liter per second, 0.008. So my first time was 0.009, now it's 0.008. And again, to get to my oxygen, okay, it's happening 3/2 times as much, because for every times 2 of these go away, 3 of these are formed. So times 3/2, and this would be, I should be able to do that. Okay, 2 goes into 8 4 times, and 4 times 3 is 12, so 0.012 moles per liter per second. And that would be my answer for here. Now notice that those two rates, okay, of appearance are positive numbers. Okay, and these two rates, since they're going away, are negative numbers. 0.008 moles per liter per second, 0.009 moles per liter per second. So again, the whole idea is, it's just the change in the concentration over the change in time, and then we can take into account the fact that the mole ratios to figure out the other chemical. If we know one chemical in a reaction, we can figure out the rates of the other chemicals. Okay, over to here. We have kinetic data here. So find the rate law for this reaction. Well, rate laws start off really easy. All you have to do is say rate, just put that word rate, equals K, and that's called the specific rate constant, times the concentration of each one of the reactants, so the concentration of pH3 raised to some power, times the concentration of O2 raised to some power. Now our job then is to figure out X and figure out Y. Those are called the orders of those two chemical reactions. And then we're going to calculate K, but that's going to happen in step B. So this is information collected of trial 1, 2, and 3, saying if we started with 0.01 mole per liter of pH3 and 0.1 of the O2, if we started with those, then this is the rate. It's not labeled rate, but we know that it's the rate of the disappearance of O2 because it's the change in concentration of O2. Now in this case we don't really need to put in a negative sign because of the fact that we know that this stuff is disappearing. Now what happens is, although it probably would make sense to call those negatives, what happens here, we're saying we're changing this concentration. Now if we take 1 and 2 and compare those, we say, well, oxygen is not changing at all, so any change in the rate must be due to the pH3. So if I compare 2 versus 1, I can see my pH3 has doubled, so this concentration has doubled, and when that happens, I can see 4.2 versus 2.1, okay, still both times 10 to the minus 2, then that means this rate has doubled. So if I double the concentration of my pH3 and the rate doubles, then I know this value of X must be 1. It has to be 1, it has to be first order. Because if it was a 2, okay, then if I doubled the concentration, it would quadruple the rate. And if I tripled the concentration, it would be 3 squared to be 9 times the rate. Okay, so the rate is not changing. This O2, since its concentration is not changing, then I know any change in rate must be due to the change in pH3, so I'm able to figure out X. Now I need a situation where this one's not changing, so 2 and 3 would be good ones to look at. And what happens here is that my concentration of O3 is tripled. Okay, now what's happening here with my rates? Well, this is 10 to the minus 1, and this is 10 to the minus 2, so I have to be a little careful. And what I officially did when I was working back with trial 1 and 2, I just took trial 2 and divided by trial 1, and I could do that in my head. Okay, this one I'm going to do it with a calculator real quick. So what I'm going to calculate is 3.8 times 10 to the negative 1 divided by 4.2 times 10 to the negative 2. And I should be able to do that in my head, but I'm not gonna. Okay, I'm going to divide those two and see what number I get. Now when I do that, what I officially did, what I typed in, I put 0.38 divided by 0.042, and what I got was something really close to 9.0476, but really close to 9. So what that means is I tripled this concentration and my rate went up by 9 times, so that means this number here must be a 2. So I would say that my reaction is second order with respect to oxygen and is first order with respect to pH 3. So let's go back and finish the question. Let's write our rate law. So the rate law is rate equals K times the concentration of pH 3 to the first power times the concentration of O2 to the second power. And that is my rate law for this reaction. Now, part B says find the value of the rate constant K and include units. Okay, well, that's really just an algebra problem. So the first thing I'm going to do is to take my rate law and I'm going to go back and just solve for K. So I'm going to say K equals, and you can see what's going to happen, it's going to be the rate divided by the concentration of pH 3 to the first power and the concentration of O2 squared. Now I'm going to put some numbers in, and the idea is it shouldn't really matter which numbers I use from my equation because, they all should give me the same value of K. K should be a constant. So I'm going to use the top numbers because they look pretty easy. So what I'm going to say is 0.1, 0.1, and 2.1 times 10 to the minus 2. So my top number here is 2.1 times 10 to the negative 2, and that's moles per liter per second, divided by, 0.1, remind myself, yes, 0.1, times 0.1 squared, and so that's going to be molarity, 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 molarity cubed. So my number here, I'm going to divide by 0.1, so that's like multiplying by 10. So that would be 21. And I have a molarity on top, and I have 3 molarities on the bottom. So that's going to be molarity to the minus 2 seconds to the minus 1. And that would be my answer. So that's the value of K, and that's my units. Now for trial 2, what is the rate of disappearance of pH 3? So for trial 2, what's the rate of disappearance of pH 3? Well, here's trial 2. So the rate of disappearance of oxygen is 4.2 times 10 to the minus 2. So what about the pH 3? Well, since there are 4 of O2s for every 2 pH 3s, my pH 3 must be going away at half the rate that my O2 is. So instead of being 4.2 times 10 to the minus 2, it should be half of that. So I would write that officially. So 4.2 times 10 to the negative 2 moles per liter per second, times the fact that I'm saying 2 moles, so 4 moles of O2 for every 2 moles of pH 3. So my rate is going to be 2.1 times 10 to the negative 2 moles per liter per second, and since this is going away, I'm going to call that negative, because it's being used up. And I think that's all the prep problems.